In this video, we are going to discuss problem based on a uniform rod supported by a metal wire in static equilibrium. The question says the left end of a uniform rod of mass 3 kg and length 1.50 meter is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. The right end of the rod is supported by a metal wire that makes an angle of 30 degrees with the rod. Calculate the tension in the metal wire. So here you have a rod which has a mass m of 3 kg and the length of the rod is 1.50 meter. It is supported by a metal wire which makes an angle theta equals 30 degree with the rod, and we need to calculate the tension in the wire. Now let us first understand all the forces acting over here. So the first force is the force due to gravity on the rod, which will act along the center of mass of the rod. So we can show force due to gravity Fg. Then we show the tension in the wire pointing towards the suspension point. And since the rod is in static equilibrium, sum of torque produced by these two forces must be zero. So I can write net torque to be equal to zero. Now what kind of torque do these forces produce? Since Fg is pulling the rod downward, it will produce a clockwise torque, whereas the tension in the wire will produce a counterclockwise torque. And if the net torque is zero, that means torque which is counterclockwise must be equal to torque which is clockwise. Now, how do we calculate torque? Torque can be written as a product of R F sine theta, where F is the force producing the torque, R is the distance of that force from the axis of rotation, and theta is the angle between them. So in our situation, the two forces producing torque is T and Fg. The axis of rotation is at the hinge. So distance of Fg from the axis of rotation, I will call it as R1. And R1, since Fg is acting at the center of mass of the rod, which is at the center, R1 will be length of the rod by 2. Tension on the other hand is acting at one of the end of the rod as the wire is connected towards the other end. So its distance from the axis of rotation we will call as R2, which is nothing but the length of the rod. So R2 will be L. Tension T is making an angle of theta equals 30 degree with the rod. So we write theta 2 for tension as 30. Fg on the other hand is making an angle of 90 with the rod. So we write the angle theta 1 as 90. So let's substitute here. Counterclockwise torque we can write as R2. The force acting is tension T sine theta 2. Clockwise torque because of Fg will be R1. Force Fg into sine theta 1. I want to find the tension T, so let's divide by R2 and sine theta 2. I find T as R1 Fg sine theta 1 over R2 sine theta 2. Now R1 is nothing but L by 2, so I write this as L by 2. Fg can be written as m times g. Sine theta 1 is 90, so I write this as sine 90 over R2 is the length L of the rod into sine theta 2. Now we can substitute the values. If you want, you can cancel off the L over here or just substitute the numbers and solve for T. So we write T to be equal to length of the rod is 1.50 over 2 times mass of the rod is 3 kg. G is 9.81. Sine 90 is 1 over again length of the rod which is 1.50 into sine 30. Now when you're calculating the value of tension, make sure your calculator is in degree mode because all of these angles are measured in degree. And when you solve this, you get the tension in the string to be equal to 29.43 Newton. Now let's discuss part B. The metal wire that supports the uniform rod is cut near the end of the rod. The rotational inertia of the rod about the center of mass is ml square by 12. Calculate in the first part the rotational inertia of the rod about the hinge. So let's look at the first part here. We have been given the rotational inertia of the rod about its center of mass. Center of mass of the rod is at the center. So I have ICM, which is rotational inertia about the center of mass. And ICM is given as ml square by 12. And I need to find the rotational inertia about the hinge. So I need to find the moment of inertia I at an axis which is parallel to center of mass. So I will call this as I parallel. Now we know from parallel axis theorem, I can find moment of inertia at any parallel axis to center of mass by adding moment of inertia at center of mass plus m times d square, where m will be the mass of the rod and d is the distance between these two axes. And since the center of mass lies at the center of the rod, d in our situation will be L by 2, where L is the length of the rod. So now let's substitute. We have ICM as ml squared by 12 plus md is L by 2 squared. That gives you ml squared by 12 plus m square of L will be L squared, square of 2 will be 4. Let's take ml squared as common and you're left with 1 over 12 plus 1 over 4. And when you solve this, you get I parallel or moment of inertia about an axis passing through the hinge to be equal to 1 over 3 ml squared. So we can substitute the values here. We get 1 over 3. Mass of the rod is 3 kilogram. Length of the rod is 1.5 squared. That gives you the value of moment of inertia to be equal to 2.25 kg meter squared. Next, in part 2 of the question, they want you to find the initial angular acceleration of the rod about the hinge. Now, if you cut the metal wire, there is no force to support the weight of the rod. And the force due to gravity Fg, which is acting at the point of center of mass, will pull the rod downward, thus producing a clockwise torque. The rod will no longer be in a state of static equilibrium and we can no longer write the net torque to be equal to 0. So I will write the net torque to be equal to I times alpha, where I will be the moment of inertia of the rod along the axis of rotation, which is I parallel here at the hinge, and alpha is its angular acceleration. We need to find angular acceleration, so let's rearrange the term. I can write alpha to be equal to tau net over I parallel. I parallel we have already calculated in the first part. We will now just calculate the torque. So we get alpha equals, torque can be written as Rf sine theta over I parallel. The force that is producing the torque is force due to gravity Fg, and the distance R is its distance from the axis of rotation, which is d, and d we took as L by 2. So let's substitute. R will be L over 2. Force is Fg, which is m into g. Theta is 90 as the angle between force due to gravity and rod is 90. So sine 90 over I parallel we found to be 2.25. Now let's substitute everything. L is 1.50 over 2. Mass of the rod is 3. G is 9.81. Sine 90 is 1 over 2.25. And that gives me the value of alpha to be equal to 9.81 radian per second squared.